right, textbooks out, open to page 18. You did problem 15, which was, I think, 6 different formulas or literal equations you were supposed to solve for one of the other letters. So I'm going to take a look at that very quickly. And then also you had 4 questions to answer from page 31 in your text. Good, all right. Let's go ahead and take a look at page 18, problem 15 first of all. You were given in number 15a this formula for gravitational force. F is equal to G times m sub 1, m sub 2 all over r squared. They wanted you to solve for the r. Now, my recommendation right off that bat would be if you see a quantity in front of or behind, in this case in front of, a fraction, my suggestion, class, was to move it to the top. Move it to the numerator. So I'm going to do this the lazy mathematician way, and now you see the G is in the numerator. Now, what I'm solving for is in a denominator. And I said that if what you're solving for is in a denominator, the quickest way to get it out would be, Audrey, to... Ooh. Michael? It's that thing that they learned that you didn't yet. Switch it. We call it... Do you remember, Audrey? Kendall. Alternate. Imagine the f being over 1 and alternate the extremes with each other. So that gives you now the r squared where the f was, and the g m sub 1, m sub 2, now all over the f. Does that make sense? So a quick alternation. Now you could multiply and then divide, but it's quicker to alternate. And now, to finish, all I have to do, Kendall, is to take the square root of both sides. So my answer for the r is going to be?
The square root of g and 1 into all over f.
Minus a point.
Positive
negative square root of g m1 m2 all over f. How many had this for this problem? Maybe maybe with or without the positive negative minus a point, but you have the main thing. Questions on this? Does it make sense now how to work it through? So a couple little strategy tips that we had talked about that you can use there. Similarly, on letter B, we're actually going to look at this today. Rho, it looks like a P, but it's the Greek letter rho. It's their equivalent of an R. Equals m over v, and we're trying to get the v by itself. Well, Audrey, coming back to you, what's the quick way to get something out of a denominator? Alternate. So if the rho were over 1, this would be a numerator, this would be a denominator, or antecedent consequent, or the extremes. And alternation transformation, we can just switch them, right? To get?
V equals mp over v.
Over, and it's technically not p, it's the Greek letter rho, but m over rho. There we go. It looks like a p. V equals m over rho. How many had that answer for this one here? Again, is it wrong to multiply both sides by v and then divide the rho away? It's not, but this is quicker. Let's take a look at the next one. We had d is equal to v sub it plus 1/2 at squared, solving for the v sub I. Michael?
Subtract 1/2 at squared.
Yeah, move this entire term over. Now, you might be thinking, I hate fractions. But the fraction is in no way affecting the v sub I, is it? So I'm not going to get rid of the fraction. I'm going to bring it over, you said, as a negative. Or I think you actually said subtract it. Either way you want to think of it's fine. That gets the v sub it by itself. And now to finish, I simply divide both sides by t. Obviously, here it cancels away. Now, the only downside to not clearing the fraction is, do you see we have a bit of a complex fraction going here? There's a fraction within the numerator. You're going to be using your calculator to do things like that, so I would say it's fine to leave your answer like this. However, if you didn't want the complex fraction, is it wrong to multiply by 2? No. You get 2d equals 2v sub it plus cancel with the 1/2 at squared. Then you subtract the at squared away. Then instead of just dividing the t, you divide by 2t. And this is actually the exact same thing as this. So either answer is correct. How many had one of those two answers for this one? Excellent. How many had the first one that we did? It's easiest, right? But the other's not wrong, and at least there's no complex fraction. Looking at the next, we have v is equal to the square root of b over rho. There's that rho again. And we're solving for the b. What do we need to do on this one? Let's go back to Kendall.
You can take this, square the square root.
Good, square the square root. Or really, we don't just square just the square root. We square both sides. There we go. Square both sides. But when you do square the square root, you get the radical. So on the right, I just have b over rho. And on the left-hand side, v squared. Now to finish getting the b by itself,
you can
multiply by rho on both sides. So I end up with b is equal to v squared rho, or rho v squared, either way. All right. How many had v squared rho as your answer? Questions on this? All right. Let's take a look at the next one. Oh, here it is again. F is equal to g m sub 1 m sub 2 all over r squared. But this time I'm solving for the m sub 1. All right. Audrey, walk us through.
You lift g to the top.
There's three things with the m sub 1, right? The g, the m sub 2, and the r squared. Which one of the three is the least attached?
R squared.
The r squared. How do we get rid of it?
Multiply it
By
by
both sides. Okay, so that here it cancels. So on the right now, I only have
and g and then and 2.
There we go. And on the right, we have
F r squared.
fr squared. All right. By the way, technically, we could have done this even without the other, or if we put this over 1 cross multiplying, would have gotten us to the same point. So there's three different ways we could have gotten to this point. Now what to get m sub 1 by itself?
You divide by g and 2.
Good. Divide by g m sub 2, and there we go. There's my answer for m sub 1. How many had fr squared over g m sub 2 as your answer for m sub 1? And the last one was really easy. F equals ma. And we're solving for the a. And Michael.
Alternate. No, you just divide the m.
Just divide the m from both sides. And so my answer is a equals f over m. How many had that four-letter f? All right. Questions at all on the literal equations? Questions at all on the literal equations? All right, let's quickly review some other things. We talked about Sig Figs. Really, the only big issue with Sig Figs class as you're calculating them or determining how many there are is to know what to do about zeros, right? If a 0 is to the right of a number, class, is it significant? Always, sometimes, never. Sometimes, only if there's a decimal. If the 0 is to the left of a number, is it significant? Always, sometimes, never. Never. If it's in the middle of a number, there's actual digits around the 0. Is it significant?
Yes.
Always, right? If we're adding and subtracting, and I've got to round my answer to Sig Figs, how do I determine the significant place or significance?
The place of least significance.
Place value of least significance. If I'm multiplying and dividing, how do I figure out how to round my answer?
Number of least significance.
Number with least significant, fewest significant digits in it. If I'm adding and subtracting values with units, I would need to make sure adding or subtracting values that have units on them.
Make them the same.
They'd have to be the same. What if there's no way to make them the same?
Okay.
Then you can't add or subtract anyway because they're not even like quantities. What if I'm multiplying and dividing? Yeah, just multiply and divide the units, right? Now, if they're like quantities, then you have to make sure you have the same units. If they are the same units and you multiply, what will you have?
Squared.
Units squared. What if you're dividing and you have the same units?
Zero.
They'll cancel. How many feet in a meter approximately, Kendall? How many seconds in an hour, Audrey?
3,600.
3,600. How many feet in a mile, Michael?
5,280.
5,280. If I'm looking at a series of measurements, I'm doing a lot of tests, and maybe I do 100 tests, and I want to see how close the values are to each other, how consistent my answers are in my various tests. If my answers are really consistent with each other, we would say my tests are precise. Now the hard part is to know whether or not an answer is exactly right. The correctness or exactness is called Accuracy. And the reason we do so many tests is if they are precise and you keep getting the same value or pretty much the same value over and over again, you can determine, okay, this is probably the accurate answer. But it's hard to know exactly what that is when you're the one doing the test. We said mistakes happen. What do we call mistakes when we're doing tests? Error, right? And error that you can't eliminate because you can't really plan for it. Random error. But if you're doing something wrong, you're using a bad instrument or you're doing the process wrong, systematic error. Clear test, except for a clean sheet of paper, pencil, calculator, clean sheet of paper, pencil, calculator.
I have my calculator, but it's in my locker.
Do you want to rent or do you want to use your free one?
I use my calculator.
Rats. Taking profits. It's like taking food right off the table of my children. Okay, that's not real. 25 cents could buy a sauce pack at Burger King. In the good old days when sauce packs just asked for however many, they just gave them to you. Not anymore. Not anymore. First last name at the top of your paper, along with today's date. First and last name at the top of your paper, along with today's date. And today is 8/16/22. 8/16/22. And this is quiz 2. First and last name at the top of your paper, along with today's date. I was kidding, Audrey. You're not really taking food off the kids' table. You're taking a sauce pack level that they could have gotten at Burger King. That's all. All right. First last name, 8/16/22, today's date. And this is quiz 2. First 7 questions, just answer the questions. And then you've got some problems to work out. Be sure when you work out the problems, you round to Sig Figs appropriately on numbers 8 through 12. Use units as needed as well. But taking the time to work through those and use the quiz copy as a cover sheet. So 5, 6, 7, you're just telling how many Sig Figs are there. You're not rewriting with Eli, so you're just telling how many Sig Figs are there. Yep. So is it 1, is it 2, 3, however many? finishing up in the next few minutes. About 1 more minute to be finishing up. We'll take a look at these tomorrow. For now, if you would go and get your textbooks out again and open to page 31. And let's go and take a look at your homework that you did, the other part of your homework, as we began reading into chapter 2. So page 31 in your textbooks, you answered questions 1, 2, 3, and 13. Get the homework back out again. Questions 1, 2, 3, and 13. Question number 1. How is matter defined, Audrey?
Matter is defined as anything that has mass and takes up space.
Excellent. Anything that has mass and takes up space. Number 2. How did Newton describe the property of inertia, Michael?
Newton describes inertia as matter resisting change.
Good. Resisting change in motion specifically. Good. He stated another way. I'm curious to see if Kendall had this written down. What did you have?
Number 2.
Yeah.
Newton described the property of inertia as matter at rest will remain at rest and not in motion moving in a straight line.
At a constant speed. Good. So matter tends to, if it's at rest, tends to remain at rest. If it's in motion, it tends to remain in motion in a straight line at a constant speed, unless some other force acts upon it. But in general, matter resists a change in its motion, is an easy way to put it. Number 3, distinguish between mass and weight. Audrey?
Mass represents how much inertia an object has or how much force is required to change the object's state of motion. Weight represents the amount of force that Earth's gravity exerts on an object's mass.
Good, excellent, very good. Number 13, describe each of the 4 states of matter. And I'm not sure that we'll get to this today. Kendall?
A solid has a defined shape and volume. A liquid has volume but not a shape. Gas has neither a shape nor a volume, and plasma exists only at high temperatures in which enough particles have enough energy to separate.
All right, so we'll go ahead and take a look at states of matter, probably more tomorrow. Good, go and set the homework aside. Back to your notes now. We said physics is defined as the interaction between 2 things. What are they, Michael?
Matter and energy.
Matter and energy. So we're going to spend a lot of time talking about energy in this class. To me, that's where the physics really gets fun. Unfortunately, before we get to that, we need to make sure we have a good understanding of matter, and you spent a lot of time in chemistry talking about matter in great detail. We're not going to go in that great detail, but we will spend the next 4 chapters talking about matter. So let's go and get this definition in your notes. It's a definition you're familiar with already, I'm sure, but matter, M-A-T-T-E-R, is defined as anything that has mass and takes up space. Anything that has mass and takes up space. So here's the question. Are you matter? Yeah, you have mass, you take up space. Now, some of you don't matter much. I mean, don't have much matter, but you matter a great deal to us, Kendall. You really do. But all of us have a different amount of mass. We take up different amounts of space, right? But all of us have mass and take up space. Can you think of something that isn't matter? Call them out. Well, see, that's interesting that you mentioned that, because they believe now that at the speed of light there is a negligible amount of mass to every photon. Yeah, it's really weird. Relativity gets into that. But for a lot of years they felt that light wasn't necessarily matter, and I kind of tend to agree with you. Something else that isn't matter. No mass takes up no space. Sound. Now, the sound is a wave that carries energy through particles, right? If you have no particles, if you have no matter, sound won't travel, right? For about sound can't travel through a vacuum. The kid was reading through his book, and he's like, so Uncle, got a question for you here. If you're in a vacuum, can you hear anything? And the uncle's like, I don't know, depends on if the vacuum's on or off. But anyway, if it's on, you probably don't hear much of it. Anyway, just kidding. So sound would be something that relies upon matter, but itself is not matter. That's something else that would not be matter. Heat. Okay, heat, that's true. Heat requires some source that is matter to give it off, but heat itself, not matter. It's simply energy that flows from particles to other particles. How about something maybe even outside the scope of science, or attempts to be outside the scope of science? How about things like thoughts? Matter? No. Now they start from the brain, which is matter, right? But thoughts themselves are not matter. They try to equate them to brain waves or radio waves kind of thing, but thoughts themselves are not matter. Emotions, they're not matter, right? And people try to study emotions and that kind of thing. That's a dangerous study. Yeah, there's lots of things outside the realm. And the reason I bring that up is because there is a side of society that says, if I can't see, taste, feel, smell, touch, it doesn't exist and it does not matter. Well, it may not be matter, but doesn't love matter? Love's important, but love's not matter. Right? There's a whole realm of things that we know exist, absolutely know they exist, that aren't necessarily tangible physical matter, right? So don't fall into that trap. The next term in your notes, inertia. Inertia. The tendency of matter to resist a change in its motion. The tendency of matter to resist a change in its motion. Now, it doesn't mean that matter won't change its motion, it just means it resists it. Which implies then that for matter to change its motion, something must cause the change, some force. For instance, when your alarm goes off, the force of inertia is strong with this one, right? The tendency of matter at rest is to remain at rest. The outside force is actually not the alarm clock going off. It's your response to the alarm clock, right? You generate a force to reach over and smash it with one hand, right? Or perhaps to hit the snooze button. And then 5 minutes later or 7 minutes later, depending on how you have it set up, you hit the snooze button again. And again. Anyone guilty like that? Any of you, the alarm goes off and man, you're up and at it. You are ready to go. Audrey is morning person. That's great. Very rarely does that happen for me, but you're ready to go. Or in some cases, the force is heaving the alarm clock across the room. Maybe if you have if you have younger siblings, maybe the outside force is them coming into your room and shaking you awake because the alarm clock is now in pieces next to you. Whatever the case may be, but you have to exert some force to get yourself out of the bed. Maybe when you were younger, your parents would drag you out of bed. I don't know. Any of you do that to younger siblings? All right, so you assist in getting younger siblings up and at them.
We have a dog.
You have a dog. All right, even better. All right, so there's some outside force that gets your matter that's at rest to no longer be at rest. Also, matter in motion tends to remain in motion. If you're walking down the hallway, right, you have this inertia. We think of it as momentum as well in a sense, but you have this forward movement that would continue unless some outside force acts upon it, like your legs, brain telling your legs, reverse engines, we're going to stop. Or there's a wall that you might run into, or maybe somebody else that you bump into as you try to get through a crowded hallway to try to get to class on time. And it's not your fault you're late, it's theirs because they were in your way. But matter that is in motion tends to retain its motion. Were you to be in a vacuum, free of frictional forces for your feet, right, as you're walking down the hallway, then if you were in motion, you would just keep on going. Think of an air hockey table. I mean, you played air hockey, okay, and the puck just kind of keeps on moving just fine until some force acts upon it because there's virtually no friction, right? The force is your force, and then it just kind of goes. Now, obviously, air hockey table is a bad example because at rest, it starts moving because of the air currents on the table, right? But if you were in space, right, you throw a baseball, it's just going to keep going at a straight line at a constant speed until eventually it hits something because it's pretty much free of outside forces. Mass is an interesting term. There's a couple definitions of mass. The most easily understood is the one you had in your younger years. I want you to go and get it down. It's not in your textbook, but it's the amount of matter contained in an object. The amount of matter contained in an object. How much stuff is in that object? That's one way to think of mass. But the book gives a different definition of mass. The amount of inertia an object possesses. Get that definition down as well. The amount of inertia an object possesses. Think of it this way. If Andrew, he's my 18-month-old, if Andrew is crying or maybe he's sound asleep and we need to get out of the house quickly or something. Okay, let's just say for some reason I need to get him out of bed. Okay? He has a certain amount of mass, right? There's a certain amount of stuff in his body. Now, Timothy is 5.5, going on 6 very soon. Okay, he's got a lot more stuff in his body. For me to pick up Andrew is easier than picking up Timothy. There's less to pick up. And another way to think of it, though, is inertia has less of a hold on Andrew, right? He does resist a change in its motion. It does take an outside force to cause him to rise out of his bed. But it takes less of a force to cause Andrew to rise out of his bed than Timothy. Inertia has less of an impact. Also this, if Andrew's waddling down the hallway, okay, tottering down the hallway, toddling whatever he's doing down the hallway, it's very easy for me to stop Andrew. Stick one arm out, and with very little effort, I stop Andrew's motion. Timothy, stick one arm out. I can still stop his motion, but it takes a little bit more. And now imagine Michael going down the hallway, even at the same speed that my children might run. Okay, so obviously he's capable of running faster, but let's suppose he were merely running at the speed of my children. It would still take a lot more effort to stop him. Why? He's got a greater amount of inertia. He's got a greater tendency to retain his motion, therefore it takes greater force on my part to stop him. Why? Because there's more stuff in him than there is in my kids. He's bigger, right? So there's 2 ways to think of mass. Now, mass is not the same as weight. Weight is simply the measure of Earth, the force that Earth's gravity exerts on an object's mass. That kind of came out a little. Let's reset, rewind. Weight is the amount of force Earth's gravity exerts upon an object's mass. Now, it makes sense, doesn't it? If you have more mass, Earth's gravity is going to pull on you more strongly. There's going to be a greater amount of force. So yes, the more mass that is in your body, the more mass you have, the greater amount you will weigh. But the key to this definition is Earth's gravity can pull differently in different places, right? For instance, at the top of Mount Everest, Earth's gravity is not as strong. So if you want a weight loss program, just go to the top of Mount Everest. You'll lose some body parts due to frostbite and amputation. That'll help you lose weight. You'll exercise and burn calories. That'll help you lose weight. And gravity's just not as strong up there. If you wanted to gain weight, you could go to the North or South Pole. Now, you'd be cold and you'd gain weight simply by putting on heavy equipment, but also Earth's gravity is a little stronger there, so you would weigh a little bit more. At the equator, you'd weigh a little bit less than you would here, though not much less. It's marginally different. Certainly, though, if you went to the moon, and that's usually the classic example, isn't it? You would lose a lot of weight there. Gravity's not as strong on the moon. Okay, so hence, by the way, kind of a cool simulator effect on race car at different places, and how depending on how gravity pulls on the race car, it's kind of cool to see like animation of what it would be. I didn't bring that in. Maybe I should one time. But anyway, but kind of cool to see the difference that gravity plays. But gravity just refers to the pull of gravity on your mass. It doesn't necessarily refer to the same thing as mass, though the two are very connected. Questions on that? This is one of the hard things, by the way, about the U.S. customary system, is weight is measured in pounds. That's a force. It's not technically a mass. Where in the international system, the SI, mass is in kilograms, force is measured in a separate unit. So while kilograms might be a good indicator of how much weight you would have, it's technically a measure of mass. Newtons would be our measure of weight. We'll get to that a little bit later on. Now, we understand this as well, though, right? You've heard the old saying, which weighs more, a pound of feathers or a pound of lead, right? Well, obviously, they both weigh a pound. It's just a pound of feathers would be a big box, and a pound of lead would be a much smaller amount, correct? They have the same weight. Therefore, if they're on the same point on Earth, they would have the same mass for Earth's gravity to pull the same upon them. But they don't take up the same amount of space. Right? And you've probably seen this before, right? Working with different types of wood. How many are aware different types of wood have different amounts of weight? For instance, when you made little gliders, how many had little gliders as kids throw them through the air? They fly. Made of something called balsa wood. Really lightweight wood. Well, it's actually really low density wood. Oak wood glider would weigh considerably more because it has considerably more mass in the same amount of space. Mass compared to the amount of space is something called density. Density. Definition of density is the ratio of an object's mass to its volume. The ratio of an object's mass to its volume. Another good example of this, I would say, would be bowling balls. How many have been bowling before? I assume all of you have been bowling. Okay. And you know this, all the bowling balls are the same size, right? You go to the rack, you don't look for a smaller bowling ball. They're all the same size. But you might look for a different weight of bowling ball, right? Well, how can they all be the same size and yet weigh different amounts? Well, less stuff packed inside. I don't actually know if it's hollow space or if they make it of a different substance. I suspect it's hollow space in the middle. They really make them out of just different substances as they go. All right, so they all have different weights, but they have the same amount of size. That's because they all have different densities. The equation for density is literally the definition. We're going to represent density, not with the letter D, because that would make too much sense, but with the Greek letter rho. Density, rho, is equal to mass, lowercase m, over volume, capital V. And literally your formula is the definition. Density is the ratio of an object's mass to its volume. We're going to measure mass. The standard SI unit is kilograms, or we could, in some cases, use simply grams if we're dealing with smaller samples. Volume. It could be measured in liters, but oftentimes we'll measure it in cubic units, either cubic meters or cubic centimeters. Remembering then that when you divide quantities, you must also divide the units. Density is going to be measured typically in grams per cubic centimeter or in kilograms per cubic meter. In this chapter, we're going to use the grams per cubic centimeter because we'll be dealing with small sample sizes. So we'll use units that make it easy to work with that. In later chapters, we'll use kilograms per cubic meter. So density, mass per unit volume, the ratio of mass to volume, grams per cubic centimeter or kilograms per cubic meter. Now here's the question. Michael has a certain amount of density, right? All of us have a certain amount of density. His dad might contend that he's very dense. But this may or may not be true, right? Who's to determine whether something is dense or not dense, right? To compare density, you have to have some kind of standard to compare to, right? For instance, as Christians, we have a standard to compare to, and that is the Bible and really the righteousness of Jesus Christ. And the problem is we all fall short. That's why we need a Savior, right? Well, in the case of density, we have a standard that we can compare to, and when we compare to a standard, we have something called specific gravity. Its alternate term is relative density, which I actually think makes a whole lot more sense. But the older, more standard term is specific gravity. But if you want to, in parentheses, put relative density. The equation for specific gravity, or relative density, is quite frankly, you compare the density or rho of some sample that you're considering, maybe it's Michael, to the density of whatever the standard would be. The density of the sample compared to the density of the standard. Now, if you look in your textbooks at page 22, try 21. Page 21, you see a table of different densities. And there's all different densities. We've got hydrogen as the lightest density listed. We have osmium as the highest density listed. There's what, I don't know, 20, 30, something different densities listed there. But what's the standard? Well, the standard, if you're dealing with a solid or a liquid, we'll compare them to pure water. Pure water is the standard. If something is more dense than water, we would say it's dense. If something is less dense than water, we would say it's not. Why do you think water is the standard for both solids and liquids?
Substance can do that.
It's pretty common around here, right? And there's lots of ways to purify water, so pure water is easily accessible. Also, I think, too, it's the most abundant substance on this planet, so why not compare to water, right? So because we live on planet Earth, we have water, we compare to that. If there were aliens on Mars, anyway, I don't know, they compare to their dirt on their planet. I don't know. Anyway, but for solids and liquids, we compare to water. We also then, because mathematicians are lazy, we have also found that pure water has a density of exactly 1 gram per cubic centimeter, or 1,000 kilograms per cubic meter. We're going to be using this number for our smaller sample sizes, though. That's convenient to say, how did that work out? Well, because originally, remember, everything was based on water. They based things on that. So they came up with a kilogram based on water originally. Now, of course, it's not, but that's how things started out, that people basing things on water. So that's the reason why also that it works out nicely. I don't mind, because I don't mind dividing by 1. I like that. I'm lazy. For gases, we use a different standard, and I'm not entirely sure why. I mean, there are lots of solids that are less dense than water, lots that are more dense. There are liquids less dense than water, there are liquids more dense. Water is a good middle value as well. For gases, for some reason, the standard was chosen as the lightest of all gases, which basically means comparatively all gases are dense. But for gases, it's pure hydrogen gas. Pure hydrogen gas, which 0.000899 grams per cubic centimeter. Really unfortunate number there. Very unfortunate number to pick, but whatever. Hydrogen gas. So again, all gases, when you compare them to hydrogen, will come out relatively dense. Solids, liquids you compare to water may come out relatively dense, may not. But here's the key. If the density of our sample is in grams per cubic centimeter, and the density of the standard is in grams per cubic centimeter, when I divide grams per cubic centimeter by grams per cubic centimeter, my specific gravity is going to come out unitless. All the units will cancel. So just know for specific gravity, it's a unitless value. So if your specific gravity came out, for instance, to the number 2, just 2, no units, just 2, that means whatever your sample is twice as dense as water. A density of a specific gravity of 5 means 5 times as dense as water, or 5 times as dense as hydrogen if it's a gas. Does that make sense? All right, so that's specific gravity or relative density. You're there on page 21 already. Look at the first example problem. Read it for us if you would, Kendall. I know, usually, by the way, when we read dimensions, we read it's this by this by this, like a box that's 10 by 8 by 12 or something. So that gives us the dimensions of the piece of quartz. Now, going back in your mind to your junior high math days, the three dimensions of a box or of a block give you that object's, well, it's based on the shape, assuming it's a block shape already, gives you the volume of the box, right? You might remember that for a box, essentially, rectangular prism, volume is length times width times height. So by giving us the three dimensions, if we simply multiply all three dimensions, 5 times 2 times 1, plus we'll get the volume of the piece of quartz. 10. 5 times 2 times 1 is 10. And notice that's centimeters times centimeters times centimeters. Centimeters cubed. 10 cubic centimeters is the volume. And it says that the mass of this piece of quartz is 25 grams. The question is, what's the density of the piece of quartz? Well, what's my equation for density, Audrey?
Rho equals M over V.
Rho equals M over V. Density equals mass divided by volume. Well, if I have a mass of 25 grams and a density of 10 cubic centimeters, we could probably do this in our head class. 2.5 grams per cubic centimeter. Now, looking at the original problem, how many sig figs do we have here in all the given numbers? 2. Everything in the problem is 2 sig figs. Our answer is 2 sig figs, and we're good to go with that. The second part of the problem says find the specific gravity. Well, to find specific gravity, remember, we're going to take the density of the sample. Well, the density of my sample is the 2.5 grams per cubic centimeters, correct? And we're going to compare it to the density of the standard. Well, what state of matter is quartz? It's a solid. What's the standard for a solid, Michael?
1.
Water, which is 1.0 or 1 grams per cubic centimeter. And if I divide 2.5 grams per cubic centimeter class by 1 gram per cubic centimeter, I get 2.5 what? Just 2.5. And notice the specific gravity is the same numeric value as the density, just less the units, when you're dealing with a solid or a liquid. Questions on that? All right, look at example 2.2. Read that for us if you would, Audrey.
Silver has a density of 10.5 grams per cubic centimeter. What is the mass of a bar of silver 10.0 centimeters long, 2.50 centimeters high, and 2.00 centimeters wide?
All right, all those length, width, height, what do I need to do with them again, class? Multiply them all together to get the volume of the bar of silver. So, your seats very quickly. What is the volume of the bar of silver? 50 cubic centimeters. All right, and then it also gives me the density of silver. I'm not sure, is that on the table? Do we see silver on there? Yes, we do. Silver down toward the bottom is already on the table, but 10.5 grams per cubic centimeter. Say, wait a second, the chart only says 10.5. If you look at the top of the column, it says density, and then in parentheses it says grams per cubic centimeter. So they give you the units at the top of the chart, so they don't have to keep listing them over and over again, because, like me and all other mathematicians, the people who wrote the book are lazy. Okay, so we know the density, we know the volume, and it asks us, Audrey, to find the
mass.
It says, what is the mass of the bar of silver? Well, what is our equation for density again, Michael?
Rho equals M over V.
Right, and that's how we're going to memorize it. But if I want to solve for the mass, I need to get M by itself. And this goes back to what we just worked on in the last chapter. What would I get if I got M by itself here, Michael?
M equals rho times rho V.
M equals rho V. So I just need to multiply rho times V, density times volume. And if you multiply that there at your seats, you'll get 525. Now we need to round off to sig figs. As I look at the given numbers, in the problem, all the given numbers have how many sig figs? 3. My answer also has 3, so I'm actually good to go with the rounding I've already got. 525, and mass will be measured here in grams. Normally mass would be kilograms, but here was grams per cubic centimeter. Notice this is a denominator, times cubic centimeters, which is a numerator. Numerator and denominator cancel, and that's where I'm left with just 525 grams. Questions on that? Turn back to page 31 now. Let's take a look at a few more problems together. Page 31. Your homework was in the questions portion, but we're going to work a couple of problems here. Go ahead and read problem number 1 for us, if you would, Michael.
Gravity on the moon is only 1/6 as strong as on Earth. Earth. A, the volleyball weighs 71 newtons on Earth. What would its weight be on the moon? B,
Good. Oh, sorry.
B, how would it being on the moon affect the ball's mass?
All right, good. By the way, recognition there that N means newtons. I think that's review from your physical science days there. Bowling ball weighs 71 newtons on Earth. Well, if gravity is a sixth as strong on the moon, what would I have to do to find the weight of the bowling ball on the moon, class? 9/6. And what would be the weight of said bowling ball?
11.833.
It'd be 11.833, blah, blah, blah. How many sig figs am I allowed? I'm only allowed the 2 sig figs from the 71 newtons if we assume the 1/6 is exact. I would contend it's probably not, so I would almost lean toward 1 sig fig, but let's go with the 2, because that was in the given number here. And we'd say approximately, class, approximately 12 newtons on the moon. Then the question says, how would the ball's mass be affected by being on the moon? What do you think, Kendall? Obviously, the weight would drop considerably. Would the mass also drop considerably? No, the bowling ball still has the same amount of stuff in it, right? If somebody threw the bowling ball at you, it would be easier for them to throw it, but it would still hurt. Does that make sense? Because it still has the same amount of mass. The example I remember seeing when I was in elementary school, and this one stuck with me because it made it easy for me to picture. If you got a big old toolbox, how many dads have a big old, maybe it's a red toolbox in the garage, okay? Anyone ever tried to pick it up? Usually really heavy because there's a lot of tools in there, all right? If you tried to pick it up on the moon, it'd be easier to pick up on the moon. If the toolbox is sitting on the moon and you kick it, it hurts just as bad as if you kick it on Earth. Same amount of stuff is there, same amount of mass, still hurts if you kick it, but picking it up just became easier. Make sense? Drop down to number 3 and read that for us, Audrey.
A gold bar is 32 centimeters long, 14 centimeters wide, and 12 centimeters high. Find the mass of the gold bar in A grams and B kilograms.
All right, so again, they give us the length, the width, the height of this bar of gold at your seats. Find the volume first and call it when you've got it. 5,376 cubic centimeters. We'll wrap up as we finish this problem. And it asks us to find the mass of the bar of gold. Well, I need the mass. I know the volume. I feel like I'm missing a number here. The density. Hold your place, flip back to page 21. Let's find the density of gold from the table. What do we get? 18.3? 19.3? All right, 19.3 grams per cubic centimeters, okay? Again, what is my density equation, Kendall? I'm sorry?
MV.
Ooh, M over V. It's the ratio of mass to volume. All right, so if I want to get the M by itself, Kendall, M will equal rho V. I'll multiply both sides by V or cross multiply. And so I'll take the 19.3 times the 5,376 that's already on the calculator. And what do we get for the mass of the bar of gold?
3,756.8.
And that's in grams, right? And it said to find it in grams. It also said find it in kilograms. Well, how would I change from grams to kilograms? Move the decimal how many places? 3 places to the left, so I get 8 kilograms. Now, last thing, sig figs. Looking at the original numbers, how many sig figs am I allowed? 2. Uh-oh. How would I round the number of grams off to 2 sig figs? Well, 100,000 is correct, but 100,000 only has 1 sig fig. We're going to have to use scientific notation, so we're going to say it's approximately 1.0, there's your 2 sig figs, E5 grams. And this number with 2 sig figs would be E2 kilograms. And notice there's an E3 difference between the grams and the kilograms in our answer. All right, for homework this evening, you're going to practice with a few of these as well. I need you to read over pages 22 to 28. Read pages 22 through 28. On page 31, answer questions 6 through 9, 12, 14, 16. On page 31, answer questions 6 through 9, 12, 14, 16, and do problems 2, 4, and 6. questions 6 through 9, 12, 14, 16, problems 2, 4, and 6. All right, have a wonderful rest of your day. You are dismissed.